Every second, somewhere on Earth, a drone is watching you. Whether it's delivering a package to your door, scanning a battlefield from 20,000 feet, or hovering silently outside your window, drones have become the most disruptive flying machine since the invention of the jet engine, and yet almost nobody understands how they actually work. Not the physics that keep them in the air, not the electronics that make them think, not the engineering that allows a machine weighing less than a kilogram to fly for 30 minutes, transmit live video, and return home on its own, all without a single pilot on board. Today, we're going to change that. We're going to go inside the drone, its motors, its sensors, its flight controller, and show you exactly how this technology works, because once you understand the engineering behind a drone, you'll never look at one the same way again. Let's start with the most basic question. How does a drone stay in the air? The answer lies in one of the most elegant principles in physics, the relationship between rotating blades and air pressure. When a drone's propeller spins, it accelerates air downward. According to Newton's third law, every action produces an equal and opposite reaction, so pushing air down produces an upward force called thrust. If the thrust generated by all four propellers equals the weight of the drone hovers. If the thrust exceeds the weight, the drone climbs. If the thrust is reduced, the drone descends. This sounds simple, and in principle, it is. But the real engineering challenge isn't generating lift, it's control. A drone has no rudder, no ailerons, no moving control surfaces of any kind. So how does it turn, tilt, and maneuver through three-dimensional space with such precision? The answer is pure motor mathematics. A standard quadcopter has 4 propellers, and here's the critical detail: 2 spin clockwise and 2 spin counterclockwise. This isn't random. It's physics. When a propeller spins, it doesn't just push air, it also creates a rotational force called torque that tries to twist the entire aircraft in the opposite direction. By having opposing pairs of propellers, the torques cancel each other out, and the drone stays stable. But when the flight controller deliberately unbalances those torques, by speeding up one pair and slowing down another, the drone rotates. That rotation is called yaw, and it's just one of 3 axes the drone controls simultaneously. To move forward, the drone tilts its nose down by reducing the speed of the front motors and increasing the speed of the rear motors. This creates a difference in lift. Rear rotors push up harder, front rotors push up less, and the entire aircraft pitches forward. Once tilted, the thrust vector is no longer pointing straight up, it's pointing forward and up, like an angle, and the horizontal component of that thrust accelerates the drone in the direction it's facing. To strafe sideways, the same principle applies, but across the left and right motors. The drone rolls to one side, and the angled thrust vector pulls it laterally. Every single maneuver a drone performs, every turn, every climb, every hover, is achieved by the flight controller making thousands of tiny speed adjustments to those 4 motors every single second. And this is where the real magic happens, because making those adjustments correctly, fast enough, precisely enough, requires a brain. That brain is called the flight controller. It's a small circuit board, often no bigger than a credit card, but it contains everything the drone needs to think. At its core is a microprocessor running a control algorithm called PID, proportional, integral, derivative. This algorithm constantly compares where the drone is with where it should be, calculates the error, and adjusts the motor speeds to correct it. It does this hundreds of times per second. The flight controller receives data from multiple sensors simultaneously. The gyroscope measures rotational velocity, how fast the drone is spinning on any axis. The accelerometer measures linear acceleration, how fast it's speeding up or slowing down in any direction. Together, these 2 sensors form what's called an IMU, an inertial measurement unit, and it's the drone's inner ear. To understand why the PID algorithm is so important, think about what happens when a gust of wind hits a drone. In a fraction of a second, the wind pushes the drone off its intended position. The gyroscope detects the sudden rotation. The accelerometer detects the unwanted movement. The flight controller reads both values, calculates exactly how far the drone has deviated from where it should be, and instantly increases power to the motors on the side being pushed away, while reducing power on the opposite side. The entire correction happens in less than 5 milliseconds. Without the PID algorithm running at that speed, the drone would be completely uncontrollable in anything but perfectly calm air. The tuning of the PID values, how aggressively the drone responds to errors, is one of the most critical and technically demanding tasks in drone engineering. Too aggressive and the drone oscillates wildly. Too gentle and it drifts. The perfect tune is the difference between a drone that flies like a precision instrument and one that wobbles like it's drunk. But an IMU alone isn't enough. It can tell the drone how it's moving, but not where it is. For that, the drone uses GPS. The GPS receiver locks onto signals from multiple satellites simultaneously and triangulates the drone's position to within a few meters, sometimes centimeters with advanced systems. This is what allows a drone to hold its position perfectly in wind, to follow a pre-programmed flight path, and to return home automatically if it loses its radio link. Some drones add a barometer to measure air pressure and calculate altitude. Some add optical flow sensors, cameras pointing downward that track ground movement like a computer mouse, giving precise low-altitude positioning even when GPS is unavailable. And high-end drones add ultrasonic sensors and infrared cameras for obstacle detection. Subscribe now, because what we're about to show you next is how all of this technology comes together in ways that most people never imagined possible. All of this sensing and computing means nothing without power. And the power system of a drone is one of the most carefully engineered parts of the entire machine. Most consumer and commercial drones use lithium polymer batteries, LiPo batteries. These batteries were chosen for one reason above all others: energy density. LiPo batteries can store more energy per kilogram than almost any other rechargeable battery technology. This matters enormously in aviation, where every gram of extra weight costs you flight time and performance. A typical consumer drone battery stores between 3 and 5 amp-hours of energy at around 15 volts. That translates to roughly 45 to 75 watt-hours, enough to fly for 20 to 30 minutes, depending on wind, payload, and how aggressively the drone is flown. The motors themselves are brushless DC motors, chosen because they are lighter, more efficient, and longer-lasting than brushed motors. Each motor is controlled by an electronic speed controller, an ESC, which converts the DC power from the battery into the precise three-phase AC signal the brushless motor needs to spin at exactly the right speed. The ESC receives a signal from the flight controller 400 times per second and adjusts the motor speed accordingly. Now let's talk about the propellers themselves, because they are far more sophisticated than they appear. Drone propellers are airfoils, exactly like aircraft wings, but rotating. The cross-section of a propeller blade is curved on top and flatter on the bottom. As it spins, air flows faster over the curved upper surface and slower under the flatter lower surface. This pressure difference, described by Bernoulli's principle, generates additional lift beyond the simple Newtonian reaction force. Propeller efficiency depends on 3 variables: diameter, pitch, and RPM. A larger diameter propeller moves more air per revolution, but requires more torque to spin. A higher pitch propeller moves more air per revolution, but creates more drag. The design of a drone's propeller is always a compromise, optimized for the specific use case of that drone. A racing drone uses small, high-pitch propellers that can spin to 40,000 RPM for explosive acceleration. A cargo drone uses large, low-pitch propellers that spin more slowly, but generate enormous, efficient lift. And speaking of different use cases, the variety of drone types that exist today is extraordinary, and each one represents a completely different engineering philosophy. Racing drones are stripped to the absolute minimum. No GPS, no obstacle avoidance, no gimbal, just raw speed and agility. They weigh as little as 250 grams, accelerate from 0 to 100 kilometers per hour in under a second, and are flown entirely by human reflex using first-person video goggles. Industrial inspection drones carry specialized sensor payloads, thermal cameras, LiDAR scanners, gas detectors, and are built to operate reliably in rain, wind, and extreme temperatures. Agricultural drones carry tanks of pesticide or fertilizer and can spray an entire field autonomously in a fraction of the time it would take conventional machinery. Fixed-wing drones, which look more like traditional aircraft than quadcopters, sacrifice vertical takeoff for dramatically improved efficiency and range, capable of covering hundreds of kilometers on a single charge. Each type of drone is not just a different product, it is a fundamentally different engineering solution to a fundamentally different problem. One of the most misunderstood technologies in modern drones is the camera gimbal. Most people think of it as simply a camera mount. In reality, it's one of the most sophisticated stabilization systems ever put on a flying machine. A gimbal is a mechanical system that isolates the camera from the movements of the drone using motorized axes. A 3-axis gimbal can rotate independently on the pitch axis, tilting up and down, the roll axis, tilting side to side, and the yaw axis, rotating left and right. The gimbal's own sensors detect any movement of the drone and instantly counter-rotate the camera to compensate. If the drone is buffeted by a gust of wind and tilts 15 degrees to the right, the gimbal rotates 15 degrees to the left. The camera sees nothing. The result is video so smooth it appears to have been shot from a completely stationary platform. This is why drone footage looks so cinematic. It's not just the altitude, it's the elimination of all vibration and shake. The radio control system that connects a pilot to a drone is another engineering marvel. Modern drones typically operate on either 2.4 GHz or 5.8 GHz radio frequencies. The controller transmits commands, stick positions, button presses, to the drone several times per second. The drone's receiver interprets these signals and sends them to the flight controller, but the video feed, the live image from the drone's camera, travels in the opposite direction, from the drone back to the pilot's screen. Transmitting high-definition video over radio waves in real time requires sophisticated compression and error correction algorithms. DJI's OcuSync and similar systems achieve this by using multiple frequencies simultaneously, switching between them automatically to avoid interference. Military drones go much further, using encrypted satellite links to transmit control signals and video across thousands of kilometers. The Predator drone can be flown from a ground station in Nevada while operating over Afghanistan with a signal latency of just a few seconds. Let's talk about autonomous flight, because this is where drone technology becomes genuinely extraordinary. A modern commercial drone doesn't just respond to pilot inputs, it thinks. Its obstacle avoidance system uses a combination of stereo cameras, infrared sensors, and ultrasonic sensors to build a 3-dimensional map of its environment in real time. When it detects an obstacle, a tree, a building, another aircraft, it calculates a new flight path around it, automatically and instantaneously. Its Follow Me mode uses computer vision algorithms to identify and track a moving subject, a person, a vehicle, and adjust its position continuously to keep that subject centered in the frame. Its waypoint navigation system allows a pilot to draw a flight path on a map, define altitudes and speeds for each point, and then step back, while the drone flies the entire mission autonomously. These capabilities have turned drones from toys into tools that are now used for agricultural surveying, infrastructure inspection, search and rescue, package delivery, and military reconnaissance on a global scale. The military applications of drone technology represent perhaps the most significant transformation in the history of warfare since the invention of the aircraft itself. Modern military drones range from tiny reconnaissance quadcopters that fit in a soldier's backpack to high-altitude long-endurance platforms like the RQ-4 Global Hawk, which can fly at 60,000 feet for 34 hours and survey 100,000 square kilometers in a single mission. The MQ-9 Reaper, one of the most feared aircraft in the world, can carry 1,700 kilograms of weapons, fly for 27 hours, and strike targets with precision-guided munitions from altitudes where it cannot be seen or heard from the ground. And now, a new class of drone is emerging that changes the equation entirely: autonomous combat drones, sometimes called lethal autonomous weapons systems that can identify and engage targets without any human input. This technology exists, it is being deployed, and it raises questions about the future of warfare that no one has answered. But perhaps the most terrifying and fascinating development in military drone technology is the rise of drone swarms. A drone swarm is not simply a large number of drones flying together. It is a coordinated network of autonomous machines that share information, divide tasks, and adapt to changing conditions in real time, without any human operator directing individual units. The United States military has already demonstrated swarms of over 100 drones operating simultaneously, communicating with each other through encrypted mesh networks, each drone aware of the position and status of every other drone in the swarm. China has demonstrated swarms of over 1,000 drones performing synchronized maneuvers with millisecond precision. The military implication is profound. A swarm of small, cheap drones can overwhelm the air defense systems of even the most advanced warship or ground installation. There is no missile defense system in the world designed to intercept 500 simultaneous targets. The drone swarm is not a future threat. It is a present one. The engineering of drones has reached a point where the limiting factor is no longer technology. It's energy. Battery technology has improved dramatically over the past decade, but it still cannot match the energy density of liquid fuel. This is why the next frontier in drone engineering is hybrid propulsion, combining electric motors with small combustion engines or hydrogen fuel cells to dramatically extend flight times. Some experimental drones are already achieving flight times of several hours using hydrogen fuel cells. Others are exploring wireless power transmission, using ground-based microwave or laser systems to beam energy directly to a drone in flight, theoretically allowing indefinite endurance. The engineering challenges are enormous, but so is the incentive, because a drone that can stay airborne indefinitely changes everything. What started as a military technology has become one of the defining technologies of the 21st century. From the smartphone-connected consumer quadcopter to the satellite-linked military strike platform, the drone is a convergence of every major engineering discipline: aerodynamics, electronics, software, materials science, and artificial intelligence. The next time you see a drone in the sky, whether it's a hobbyist flying in a park, a delivery vehicle approaching your door, or a military aircraft you can barely see, you'll know exactly what's happening inside it. Thousands of calculations per second, 4 motors in perfect mathematical balance, a machine that thinks faster than any human pilot ever could. That is the drone, and it has already changed the world.